Take a look at this metal sphere. When you push a massive object, it doesn't instantly reach top speed. It fights you. It takes significant effort to get it moving and an equal amount of effort to stop it once it has momentum. In physics, we know this as physical inertia. But electrons flowing through a wire experience an almost identical kind of resistance long before any mechanical parts are involved. Notice this circuit diagram. When we send a sudden pulse of current into a coiled wire, the electricity doesn't instantly jump to full power. Instead, it struggles to build up, slowed down by expanding rings of magnetic force. As the current rises, it generates a changing magnetic field. That changing field then acts as a barrier, inducing a back EMF or electromotive force that fights back against the incoming electricity. The circuit is actively opposing any change to its current state. If the current is zero, it wants to stay at zero. If it's flowing steady, it wants to keep flowing steady. Just as mass gives physical objects mechanical inertia, this phenomenon gives circuits electrical inertia, called inductance. To understand exactly where this electrical inertia comes from, we have to zoom in closely on the structure of the wire itself. This 3D diagram shows a single loop of wire. When current flows through it, it generates a highly localized magnetic flux, represented here by those glowing vertical lines, which map the concentration of the magnetic force. According to Faraday's law of induction, if that current starts fluctuating, the resulting magnetic flux will expand and contract. That movement induces the opposing voltage, fighting the change in flow. But a single loop only creates a tiny amount of resistance. We multiply that effect by stacking multiple loops together into a tightly wound coil. Now, the magnetic flux generated by one turn of the wire doesn't just stay local. It reaches out and interacts with all the other turns in the entire coil simultaneously. Textbooks call this overlapping field flux linkage. Mathematically, it is n phi b, where n represents the number of turns. By simply taking a straight piece of copper wire and bending it into a spiral, engineers turn a weak magnetic quirk into a highly concentrated, powerful barrier against electrical fluctuations. As this animated chart illustrates, there is a perfect direct relationship at play here. As the amount of current flowing through the coil goes up, the total flux linkage scales up right alongside it. When two values move in lockstep, physicists link them into an exact equation using a constant of proportionality. That missing constant is the letter L. We drop it into the middle, and we get our final mathematical rule. N phi b equals Li. That L stands for inductance, sometimes referred to as the coefficient of self-induction. The standard international unit for measuring this specific property is the Henry, denoted by a capital H. Because L is a constant, a coil's inertia is a permanent, fixed feature of its physical design. It exists whether electricity is flowing through the copper right now, or the coil is just sitting cold on a workbench. This split-screen diagram highlights a perfect symmetry in the universe of electronics. On the left, a capacitor. On the right, an inductor. A capacitor stores an electric field. How much it can hold is dictated entirely by its geometry, the surface area of the metal plates, the distance between them, and the insulating material sandwiched inside. An inductor operates on the exact same physical logic, but for a magnetic field. Its ability to store magnetic energy is governed by strict geometric dimensions, the cross-sectional area of the loops, the total length of the coil, and the exact number of wire turns. And just like the capacitor, the internal material matters. If we slide a high permeability material, like a solid piece of soft iron, into the hollow center, the density of the magnetic flux multiplies, drastically increasing the coil's inductance. This makes inductance a precise architectural blueprint. By slightly altering the shape, length, and core material of a coil, an engineer can perfectly tune a circuit's electrical inertia. The measuring unit H honors Joseph Henry, the American physicist who first documented self-induction in the 1830s. Simultaneously, Michael Faraday was independently confirming these principles of electromagnetic induction across the Atlantic in England. Look at this early experimental apparatus. Using nothing more than simple coils and magnets, they proved that motion, electricity, and magnetism are deeply, universally intertwined. Today, those 19th century discoveries dictate the modern world. Whenever an industrial motor spins up or a massive transformer goes online, it has to fight the immense magnetic inertia of its own copper wiring. By calculating and mastering inductance, engineers harness this natural resistance. They use coils as electrical shock absorbers, smoothing out chaotic, dangerous voltage spikes into the stable, reliable power grid we depend on every single day.